Gold, as the saying goes, is where you find it. But there are some useful clues which have guided seekers of fortune for centuries. For instance, where you find quartz, gold shouldn't be very far away. Although enough heartbreak stories exist to prove there are exceptions to every rule. Until the 1880s, however, very little attention was paid to the quartz itself. Usually it was crushed for road making. But around that time, quartz, or more accurately, piezoelectric quartz crystals, began playing an important role in the field of communications, then in its infancy. In 1880, the Curie brothers first discovered the piezoelectric effect of crystals, meaning that when crystals were inserted into a circuit or device, they'll perform as a frequency controlling element. Despite many attempts at finding an alternative, nothing else has come close to matching this remarkable effect. In 1883, utilising this piezoelectric effect, the Curies devised the first voltmeter, and from there the crystal's future as a scientific tool was assured. Nowadays, quartz crystals are well known for their use in digital watches, radio transceivers, computers and microwave links. Their main asset is the ability to lock a frequency into position. For instance, radio stations occupy a fixed point on a dial. Without crystal control, the stations would wander. Commercial crystals are manufactured in vast numbers, with frequencies from 100 kHz to 150 MHz. During the Second World War, crystals played a vital role. So important, in fact, that one scientist called them the most remarkable of all tools science has given to war. And as this 40-year-old film shows, the importance of crystals was recognised by the Australian government.
Here lies one of the strangest diggings in Australia, a quartz crystal mine that during the war ranked high among the nation's top secrets. When America's consumption of quartz became so great that she could not meet her own requirements, Australia was thrown suddenly on her own resources. And when it is considered that a radio transmitter depends to a large extent on a quartz crystal oscillator for its transmission on a fixed wavelength, the value of the quartz can be clearly understood. In the old gold rush days, crystals such as these were thrown aside as worthless. All but half of 1% of the mine crystals are unsuitable, and of those chosen, all the angles of the naturally formed faces are identical. The mine is worked by two experts, Bob Terry and Ev Hughes, under the guidance of Mr. Jack Willey, whose Quartz Crystal Laboratories in Melbourne helped to save the day for Australia in a period of crucial need.
The quartz crystal industry is no less important to Australia today. Telecom Australia's research laboratories are recognised as leaders in the design, development and evaluation of high-precision piezoelectric quartz crystals. The cutting, lapping and polishing at Telecom's laboratories is carried out by a small but highly skilled team of experts. And because of the high precision requirements, this process is an exacting one. First comes the removal of the seed from the cultured quartz bar. This seed, from which the quartz grows, is of no value and has to be removed before the bar can be wafered. This is done using a phosphor-bronze diamond-impregnated saw, which slices through the centre of the crystal, effectively cutting it in two. When that operation is complete, 1/2 of the bar is prepared for a second cut. On an angle of 35 degrees 24 minutes, a single square wafer is cut at a width of 1 millimetre for testing. The wedge-shaped piece at the end is discarded, as it serves no practical use. The test wafer is then placed in what's known as an X-ray diffraction goniometer. This instrument determines the angle of the cut in relation to its Z-axis, enabling the rest of the bar to be cut accurately. Once the measurement is verified, the blade continues to finish off the bar. Normally, we would end up with about 45 wafers. The wafers on the left are now ready for the next process called loafing. Thermocement is applied to each one and they're joined together onto a loafing jig, seen here on the top right. Underneath is the loafed group with square blanks ready for grinding and lapping. On the bottom right is the same set of blanks, this time circular in shape, after the lapping and grinding process is completed. Rounding is performed on a centre grinder, similar to those used in industry. The 8 wafers, now glued together, are compressed tightly with a blank sheet of glass at either end. After an operation lasting several minutes, the square crystals are ground down to a circular shape, ready for lapping. Constant supervision with the application of liberal quantities of abrasive slurry ensures that the finished blanks are lapped and polished to a high surface finish. When the careful precision cutting and lapping of the edges is complete, the process moves to the next stage. This is known as the master lap. This machine puts an optical flat surface to the lapping machine workplates. Again, an abrasive slurry is poured onto the lapping plates to ensure a perfect optical result. We now have a workplate of the highest optical precision. See how the vertical lines move in a clockwise direction without bending when finger pressure is applied. This proves that the plate is optically flat. The next step in this complex operation is what's called the elliptical lap. The blanks are placed into the lap, coated with abrasive slurry, and the rotating motion ensures a surface as flat and as parallel as possible. Using an electronic thickness gauge, tests are made for flatness and thickness of the lapped blank. On a flat blank, there should be no movement on the gauge. Lapping on a spherical generator, however, produces a contour on the surface of the blank, giving a plano-convex type of crystal as used for high-precision quartz resonators. And measuring on an electronic scale this time indicates a maximum degree of deflection. We've now reached one of the most critical parts of the entire operation, checking the frequency of the crystal. This is done electrically within an air gap. The thicker the crystal, the lower the frequency. The blank is inserted into an impedance bridge, and reading from the counter will ensure that the blank is satisfactory. So far, so good. We're now into the next stage in the fabrication of the crystal. All the blanks we've just cut and lapped are now etch-polished in an agitator. This process continues for a few minutes while another operation is being carried out simultaneously. This is the ultrasonic cleaning of the glass bulbs, followed by the chemical cleaning of the glassware and crystal by rapid evolution of oxygen bubbles. The blanks and the glassware are now cleaned by ultraviolet irradiation in a laminar flow clean room. This is where the final careful assembly of the finished crystal takes place. The crystal is placed in a clamping vise where the thermosetting conductive cement is spotted to the edges of the blank. This enables the support wires to be soldered to the crystal. The first part of this delicate operation is to apply liquid solder to the wires and blanks, a job that can only be performed under the microscope. That done, the plating jig is assembled to hold the assembly prior to the actual gold plating. The plating jig locks the crystal assembly into place so that the gold within the filament of the evaporator assembly can be prepared for the melting process which will evaporate the liquid gold into the blank. This process takes place in the vacuum plating unit to produce the gold-plated keyhole-shape electrodes. Only two more steps remain: the encapsulation of the crystal and sealing of the evacuated assembly exhaust stem. The crystal is first installed into the flame sealing machine, followed by the actual sealing of the bulb to the envelope. Intense heat is then gradually applied to make sure the join is perfect. Within seconds, the operation is complete. The seal unit is removed and stretched to alleviate joining stresses. It's then placed in a thermally insulating container to slow down the cooling process. After cooling and inspection, the completed assembly is placed in a vacuum system. A heating hood is lowered and all contaminants are pumped out. All that remains now is for the stem of the evacuated enclosure to be cut, effectively completing the sealing operation. The completed crystal is now installed into an oven-controlled crystal oscillator. This consists of the outer container with polyurethane insulator, then vacuum flask, followed by the cylindrical heating source. Exposed is the oscillator assembly with associated circuitry. This will now become part of the precision phase-locked oscillator. It will give extremely precise frequency outputs for analog or time systems. And finally, we have the completed 5 MHz third overtone high-precision resonator. It's much stronger than its older counterpart, the 100 kHz resonator, which was fragile and had poor stability. However, the laboratories will soon be making a new type of resonator, the HC27U all-glass enclosure, which is more compact and has a mechanically more stable configuration. Although we seldom hear about it, crystal technology is responsible for many of the things we take for granted. Think about it next time you look at your digital watch or dial the time.
At the third stroke, it will be 2:53 precisely. At the third stroke, it will be 2:53 and 10 seconds. At the third stroke, it will be 2:53 and 20 seconds.